In the last section, we had a lot of vocabulary and terms to deal with, and in this section, again, we're going to have a lot of vocabulary and terms. So, unfortunately, let's go ahead and just get started. Here we have some curves, some different types of curves that are listed out, and you'll notice that the boxes here talk about them being simple, closed, polygons, convex, or concave. Well, we need to figure out what each of these means. So this is some of our vocabulary for now. Well, if you'll notice, all of these checked here are simple except for this one. So I wonder what makes it different from the others. Well, if you'll notice, these others, you can just draw them, take your pencil and start drawing them, and you never touch what you've already drawn until you get to this one. This one, if I were to draw it out, I could say, okay, here, here, here. Oops, now I've had to cross back over what I've already drawn. Well, simple means that the curve does not intersect itself except at the starting and stopping points. So that is what makes something simple or not simple. So the rest of these are simple. Now we also talk about them being closed. And closed means that the curve can be drawn starting and stopping at the same point. So you'll notice that all of these here at the bottom are closed because no matter where I start, if I say I start right here, then if I draw in this figure and then I stop at the same point that I started at. But that can't happen with these two figures here at the top. I don't stop where I started, so those two are not closed. Now for polygons. Polygons have to be simple and closed to begin with, and then we can look to see if they're possibly polygons. And polygons are shapes that are made up of line segments. So you'll notice that out of the ones that were both simple and closed, this one is not made up of line segments, so it's not a polygon. This one is not made up of line segments, it's not a polygon. This one was not simple and closed both, so we can't even talk about it being a polygon. These two are both polygons because they are simple and they are closed, and each one of them is made up of a bunch of line segments that are joined together. Now, we can talk about things being concave or convex, but they have to be simple and closed again to begin with. If they're not simple and closed, then we can't talk about them as being convex or concave. They would just have other terms that were attached to them. But what that means is for convex is they are curves that are simple and closed. And if you were to draw a line segment between any 2 points, the line segment would be completely inside the figure. So you'll notice that these two are convex, meaning no matter which 2 points I use on this curve, if I draw the line segment between it, that line segment lies entirely within the figure. Also for this one here, no matter which 2 points I use, say I use this point and this point, if I draw the line segment there, then that is enclosed completely in the shape itself, so that makes it convex. This figure here is not convex, it's concave, so that's the opposite of convex. If I were to put 2 points, like say here and here, and draw the line segment between them, then my line segment is outside of my figure. That's what makes it concave. Now we also have, dealing with polygons specifically, we have different sides of our polygons. They could have, this one just particularly has 3 sides, which makes it a triangle. And down here is listed out some of the different names of our polygons. If we have 3 sides, it's a triangle. 4 sides is a quadrilateral. 5 sides is a pentagon, and so on and so forth. So we have these sides that are the line segments that are used to make up those figures, where the line segments meet, or where we have these corners, we call those vertices. So each one is a vertex. Together, the plural would be vertices. Then you can also talk about the interior and the exterior of the polygon. The interior, of course, being inside the polygon itself, the exterior being outside of the polygon, and that interior space is also called the polygonal region. So that's pretty interesting. Now, let me scroll down here and let's continue talking about these polygons. If you were to draw a line segment between any two vertices that are not touching or not close to next to each other, the vertices that are next to each other are called adjacent vertices. And we're not talking about adjacent vertices, but any of the other vertices in a polygon, if you were to draw a line between those, that would be called a diagonal of the polygon. Each one of these angles here, and I'll draw each one of these in, each one of these angles on the inside of the polygon is called an interior angle, or they could call it an angle of the polygon. Now, here we had, if you remember in our drawing, we had number 1 here was this interior angle. If we were to extend the side of the polygon out and look at the angle that forms with the line segment of the polygon, that would be considered an exterior angle of the polygon. So that's pretty important terms to understand and to know. Let's see how much further we can get here. We also need to talk about congruence. And congruence means that two things are equal. They are the same length. Like for instance, this line segment AB is congruent to this line segment DC. They are the same measure in length. We could draw one on top of the other and they would be identical to each other. So we would say that the measure of line segment AB is the same as the measure of line segment CD, or we could just say that those two things are congruent to each other. And that symbol for congruence is an equal sign with a little squiggly line on top of it. Now we can talk about line segments being congruent. We can talk about angles being congruent also. And that helps us whenever we start talking about regular polygons, because the definition of a regular polygon is that where all the interior angles are congruent, that's called equiangular, and all the sides are congruent, that's called equilateral. So here we have a polygon with 5 sides, so that's called a pentagon. And this pentagon has 5 angles that are the exact same measure and 5 sides that are the exact same measure. That makes it considered a regular pentagon. Here we have a picture of a regular hexagon, which we have 6 sides in the hexagon, each one of the angles being exactly the same measure and each one of the sides being exactly the same measure. Now we also have some more terminology here, especially dealing with triangles. A triangle containing one right angle is called a right triangle. So here we have some examples of that. A triangle in which all the angles are acute is called an acute triangle. So every one of these, and you remember from your terminology from before, acute meant less than 90 degrees. So each one of these measures is less than 90 degrees. A triangle containing one obtuse angle is called an obtuse triangle. And remember, obtuse was more than 90 degrees. A triangle with no congruent sides, so none of these sides are the exact measure. Also, none of these angles would be the same measure. That's called a scalene triangle, so you need to know that. And a triangle that has at least two congruent sides is called an isosceles triangle. And in an isosceles triangle, the two sides here are the same measure, and these two angles across from those sides are the exact same measure as well. A triangle with three congruent sides is called an equilateral triangle, and an equilateral triangle also has three angles that are the exact same measure. A trapezoid is a quadrilateral with at least one pair of parallel sides. So even though these sides are not congruent, they're not the same measure, they are parallel to each other. Then we have a kite, which here's some examples of a kite. This is a quadrilateral, meaning four sides, with two adjacent sides congruent and the other two sides also congruent. So you'll notice that here in this kite we have these two sides are the same measure and these two sides are the same measure. And here's another picture, another example of another kite. We have an isosceles trapezoid. An isosceles trapezoid is a trapezoid with congruent base angles. So this angle and this angle would be the exact same measure. Also, those sides adjacent to them would also be the same measure, and then we would have two parallel sides also. We have a parallelogram. A parallelogram is a quadrilateral in which each pair of opposite sides is parallel. So these two sides are parallel to each other, and then these two sides are going to be parallel to each other. Now, a rectangle is a very special kind of parallelogram where we have right angles where each one of those sides meet. A rhombus is also a parallelogram, but we have two adjacent sides that are congruent to each other. So basically, your adjacent sides are equal in measure. A square is a very special kind of rhombus, so it's a parallelogram. It's a rhombus. It's also a rectangle, meaning that the we have 90-degree angles here. I couldn't get my words out. Sorry about that. And we also have these four sides that have the exact same measure. So that's very cool. Now here I've put down here some kind of a hierarchy so you can see it. We have polygons, two different types of polygons because there are more, but this is just two different types. First of all, we're going to be talking about a triangle. And when we talk about triangles, they could be either scalene or isosceles. And then isosceles triangle, a very special kind of isosceles triangle, is an equilateral triangle. And when we talk about quadrilaterals, that's kind of like our main big um, um, kind of overreaching word that we use for all of these. And then they can be broke down even further into kites or trapezoids. Trapezoids broke down into parallelograms and isosceles trapezoids, broken down further into rectangles, broken down further into squares. So we have different levels. Even though a square, we all know what that is, it's a very special kind of quadrilateral. It's a special kind of parallelogram. Okay, finally we need to talk about symmetry. And if you'll remember what symmetry is from college algebra, it's where you have like a balance. You have, if you were to be able to draw a line down the center of something, you'd have equal parts on both sides of that line. So for instance, here we have this picture of, I have no idea what this is, maybe a cloud or something like that. But if we were to draw a line straight down through the center of it here, you can and fold that over on itself, we'd have an exact picture. It's like a mirror image. So we have some different examples here of some mirror images. Now we could also rotate those, and that would be called rotational symmetries, if we could rotate the figure and have the exact same picture that we started with. So for instance, this flower here, if I were to take and just rotate this a little bit this direction, then this flower petal would end up over here, this flower petal would end up over here, and we'd have the exact same picture as we started with. This figure here, if I were to rotate it around 90 degrees, then we would have again the exact same picture that we started with. So that's called rotational symmetry, and we're going to be working a little bit with that in some of the things that you're going to be working with in your examples in your homework.